Stat 1150. This is the first video on hypothesis testing for proportions, and the good thing about this, if there is a good thing, is I'm not teaching you hypothesis testing in the beginning. This is a follow-up where we had hypothesis testing for means. So my point is you have a pretty good foundation now on how to work hypothesis testing mean problems. Well, these problems are specifically for addressing claims, status quo, what's currently believed about a percentage or a proportion. Now, the difference, if we can think about it this way, means versus proportion problems. Well, guys, I promise you I can spell, I just can't see. You think about percentages here. Now the difference in, the first thing we have to do is we have to be able to identify one of these problems versus one of these. And at the end of the day, what you do is you look for whether the average for a population value versus a percentage that's explained for a population value. Now, the technical difficulties or the technical differences are means used what's called a t-test. And a t-test used what's called the t-distribution, which is a function of the degrees of freedom. And we've seen that the degrees of freedom is really easy to find. It's just n minus 1. Now, proportions, on the other hand, use what's called a z-test. And guys, these use the z-distribution. And the z-distribution has a mean equals 0, standard deviation equal to 1. So I'm going to show you, just like I did in the means, we looked at the critical value and the p-value approach. Well, I'm going to show you the critical value and the p-value approach over here as well. And it's going to remind you of some of the stuff we did over here, but there's going to be, again, some technical differences. So let's say that we are conducting, well, let me back up a little bit. Remember when we begin a test of hypothesis, we do so by stating the null and alternative hypothesis. The null is H sub O, the alternative is H sub A. And remember, what we have is we have a parameter value always equal to some value, some number. Now, for this class, the only ones that we look at are either the mean problems or the p problems. So that's what the purpose of this video is, to look, start looking at these types of problems. Again, whatever notation goes there will always come here. Whatever value goes here will always go there. And we'll have a competing inequality that represents what we want to test. Okay? Now, let's say that we would like to test that a population proportion is 38%. And we would like to test that against p greater than 38%. Now, what I want to show you is just how would we find the critical value for the test of hypothesis. Well, just like we did before, we would draw a distribution. This all goes back to the distribution of sample proportions that we studied in the central limit theorem. And we know smack dab in the center of the distribution is the mean, but because we're modeling this problem with a z-distribution, we have mean 0, standard deviation 1. Furthermore, since we're conducting a greater than test, we know that our rejection region is going to be to the right. It's going to be a right tail test, a one tail test. It's going to be to the right of the mean. So we're going to have a rejection region out here. And everything else is going to be a fail to reject. Now, everything is about the H sub O, right? Fail to reject H sub O or reject the H sub O. So this line in the sand that we've talked about before is relative to the level of significance. So let's just say, for illustration, that our level of significance is 0.05, and that's usually the way it's going to be. So that tells us that this area to the right of my line in the sand, the Z critical, must be positive because it's to the right of 0. Now, if we were doing a less than, we'd have our critical value down here. It would be a negative number, but that's not the case in this situation. So we know it's going to be a positive number that has, in the normal distribution, the Z distribution, to the right of it 5% of our area, and to the left of it 95% of the area, because all this area has to add up to 1. Well, guys, it's really easy to find that. Again, what we need 5% of the area to the right with the distribution that has mean 0, standard deviation 1. Now to work this problem, what we'll do is we'll go to StatCrunch, which I have up here, and we'll go to Stat. We'll go to our calculator. But guys, when we have a mean, a hypothesis testing for a mean, we go to the t-distribution. But as I talked about earlier, the t-distribution isn't appropriate. The z-distribution, or the normal distribution, is what we use to model the sampling distribution for a one-sample test of hypothesis for a proportion. So we go there. We're going to have mean 0, standard deviation 1. And ultimately, easy for you to say, what we need is we need the area up in the right to be 0.05. So we can calculate that and see that that's 1.645. So going back over here, our Z critical would be positive 1.645. So our next step, if we were working this problem using the critical value approach, is to calculate the test statistic. Okay, a little bit about the test statistic. As you would expect, or at least as I would hope you would expect, well, guys, I get distracted so easily. I just received an email from one of my grad students, and I just absolutely bombed the spelling of statistics. So anyway, it's kind of funny. The test statistic, guys, for a mean, because it uses the t-distribution, is a t-value taking the x-mean minus the mean over the standard error, which is x bar minus mu, the standard deviation divided by the square root of n. Now, when we get into a proportion problem, we use a z-distribution. Somebody might say, well, why? Don't worry about why. At this point in your statistical career, if you want to go get a PhD and be a total geek like me, then you'll learn stuff like that. But right now, let's just use these as tools. These are tools we use to address problems that we may need addressed statistically in our majors or our professions. So right now, just remember, a mean, you use the t-distribution. A proportion, you use the z-distribution. So instead of a t-statistics, should make sense. We're going to use a z-statistic. Well, I'll tell you what, I can't get any more distractions than what I'm getting in this video. So, but anyway, back to the video. Instead of X bar, what would seem like a reasonable replacement in this type of problem? Well, ultimately, we're making a statement about mu, aren't we? And we're using X bar to kind of estimate that. Well, these problems down here, we're making a statement about P, and we're using a sample proportion to make an estimate about it. So it would make sense that instead of X bar, in these types of problems, we use P hat. And instead of mu, we would use P. Because that's this is the population mean. This is the population proportion. And then in the bottom, we have the standard error, but we did the standard error for this distribution here. So guys, it turns out that the standard error is the square root of P times 1 minus P over N. So what we would do is we would calculate our test statistic. We would go back to our drawing and see where it fell. If it was above 1.645, then we would fall into the rejection region. If it was to the left or lower than 1.645, we would fall into the failed to reject region. The main thing that I want you guys to know in leaving this video, and I'm going to be wrapping up here within the next 30 seconds, is you have two types of problems: hypothesis testing and confidence intervals for means and proportions. The distribution that models confidence intervals and hypothesis testing for the mean is the t-distribution, which has a t-score, a t-value. Here, proportions use the z-distribution, so we have a z-score, a z-value, a z-critical, and it's calculated by taking the sample statistic minus the parameter over the standard error in both cases. All right, gang, next video we're going to get down dirty with some hypothesis testing for proportions. We're going to look at some examples, and you're going to see how easy these things are, especially if you use the p-value approach. So, guys, have a good one.